Karolinu na půdě Karlovy univerzity. Čeká nás odpoledne plné velmi zajímavých přednášek. Zaměříme se na budoucnost energetiky a celý ten program je v angličtině, tak mi dovolte, abych tedy přešla rovnou do anglického jazyka. So, good afternoon everyone. It's my great pleasure to welcome you here in Carolinum of Charles University. This is a place that has amazing and long history, but today we are here to discuss our future. We are going to focus on future of energy, which is one of the most crucial and urgent issues of nowadays. So we are going to talk about energy transformation, integration of renewable resources, and the impact on the society and economy. We have wonderful speakers, and there will be 4 talks. After each one, there will be like 10 minutes, so you can ask your questions. Don't hesitate to ask. And before we start, I would like to invite on stage Professor Pavel Jungwirth, President of Czech Learned Society. He would like to welcome you here.
Thank you, Kateřina. Welcome, everybody. It is the mission of the Learned Society to address the most pressing, important issues. And until a few months ago, I thought this will be climate change, energy transformation, and we'll dedicate the whole day to it. Then Ukraine came, so we have 2 most important pressing issues at the moment, and we dedicate the morning to Ukraine. So we have now the future of energy for the afternoon. And I'm very much looking forward to this symposium. It will be lectures, but I think there will be also space for debate and discussion. So please be active and enjoy. Thank you very much.
Thank you very much for your introduction, and it's my great honor to introduce our first speaker. It's Professor Jutta Hansson from Darmstadt University of Technology. Please welcome. I heard you prefer to stay?
Yes,
yeah?
Yes,
okay.
yes.
So it's yours.
Okay, it's already mine. I need the pointer. Dear Mr. President, dear members of the Learned Society of the Czech Republic, dear guests, it's an honor for me to stay here and to present the transformation of the power grid. So we will make a deep dive into the electrical network, and I hope you are prepared after lunch. So, how to start? What are the main topics? I would like to introduce the German Energiewende. So what are our goals? What are we talking about? So how to transform? And my research focuses on the transmission distribution. So what has to change within our electrical network that we can reach the goals? Of course, what do we have to transmit? What do we have to distribute? We have to look at the generation and at the consumption within the network. And if there's some time left, then I would like to talk about the ongoing research at our department. What are the main challenges for the energy transformation? And I heard that there will be talks dealing exactly with this topic, so I'm only dealing with one. We have an enormous time pressure, as you will see on the next slide, because we want to avoid the climate change, and therefore we have to encourage whatever we are doing. And what are these challenges within numbers that I would like to present? But we also have conflicts with the nature, because that's what we want to do is we want to erect wind turbines, but of course the people are living there and they do not like those. And they do not like overhead lines either. Then we get a new network which is very, very complex. So we need some different chances because we have so many PV on our roofs that we have to find a way to coordinate those different generators. And this will be a big, big challenge. And then we need innovation and we need investments. And that, of course, we can only do within a reliable framework. And we see that we do not have those conditions today. So what are we intend to do? Here are some numbers, new numbers after the last election. And you see that we want to shut down the nuclear power plants end of this year. So we still have 3 nuclear power plants in the grid. And we also want to shut down the coal-fired power plants. And this we intendedly wanted to do in 2038. Now we are wanting to be faster. We want to have it within 2030. Additionally, we say, okay, we have to change our generation. So if we do not have those coal-fired power plants, then we need something else. We need PV, photovoltaic, and you see here the number 200 gigawatt within 2030. We have 2022, and I will show on the next slide how many PV we have at the moment within the network, and then you see how big this challenge is. We also say that we want to go offshore. Offshore wind, we want to have 30 gigawatt within 2030. At the moment, we have not more than 8 gigawatt installed. The other goal, which you see here on the left side, that we want to have 80% of the electrical energy consumption from renewable energies, also means that we have to erect onshore wind farms, which are not here named on the slide. And if you come up with those numbers, then there will be additional 100 gigawatt onshore, which we also need. These are the goals from the government, but we have other goals. You see here an HVDC overhead line. Who knows what the abbreviation HVDC stands for? Please be honest, I will explain if you do not know it. Okay. Sorry? High voltage direct current, exactly. So that what we need is something different than that what we have today. Today we have within our networks 50 hertz, and that what we have to do if we want to have a long transmission, and that is what we have to do from the northern part of Germany to the southern part or to the middle of Germany, then we have to use a different technology, and this is a technology without the frequency, so the frequency is 0. And this is what we have to do in the north. We have to convert the frequency from 50 to 0. Then we can transmit over a long, long line, and then we go back to our 50 hertz. And this we do with a high voltage. Therefore, this is the abbreviation high voltage direct current. We also call it our highways, which we have within our electrical network. And there are plannings ongoing, and we say that we would like to have them finished within 2027 or 2028, and this is already a big delay. The energy efficiency, so everything which we do not use, we do not have to generate or we do not have to transmit. And you see here that we have reductions within heating, but also within the electrical current. And we say it is minus 25% or minus 60%, even that one. So we have to use less energy. And this one is, of course, again, a new topic after the conflict with Ukraine. The flexibility, we spoke about the complex network, what is ongoing. You see here some cars, yes, of course, electrical cars. And it is intended that we have more than 15 million within 2030. And this, of course, is a big challenge for the network because it is current which we need for this one to charge them. And to find a different possibility, because we speak about PV, we speak about wind, and you know this is not there all the time. We need something reliable, and therefore we think one way is to have it with gas, and here you see the electrolyzer, and we want to have more than 10 gigawatt in 2030. You heard very, very high numbers, and now put them together with our electrical network. What do we need at the moment? And you see here on the left side that what we need as power, 80 gigawatt is the highest power which we need. And within 1 year, we need 600 terawatt hours, which we have within the German networks. Put that to our power plants. If we just talk about the load, 80 gigawatt, then we need for this one nuclear power plants a number of 54, if we assume a certain amount per nuclear power plant. And if we say, no, we need it the whole year, and then we know, okay, a nuclear power plant can be in operation 7,500 hours per year, then it is the same number. But this, of course, changes if we go to wind or if we go to PV. You see that the power of a single wind turbine is much smaller. We are here with 2 megawatts, which is at the moment the average. It is not the highest power rating, but if you look in average what is installed in Germany, then we are here with the 2 megawatt. And then we need 40,000 wind turbines if we just want to have the power. But if we say, no, no, we need it the whole year, then we see that, no, we do not have 7,500 hours. We only have 2,000 hours, and this is for onshore wind. And then, of course, the number goes up. The same for PV. The very small power which you see here is that what we erect on roofs per roof. So this is just 0.004 megawatt. And you see the high number, 20 millions for the power. But if we go over to the energy, this means we have more than 150,000 because we can assume that it is 1,000 hours per year with that load. Not more. To be honest, here we have the wind, and the 2,000 hours are fitting to onshore wind. If we have offshore wind, then we can increase the number. We can go up to 3,000 hours. Okay, now we have the big numbers. We know what we need, what we intend to do, what do we have within the network. And then you see on the left side again the capacity, so the load, that what we generate. We have installed a total of 217 gigawatt, and renewables has already a big part out of it, 137 gigawatt. That's a good number. It's a big effort. It's a good story which we can tell. If we go to the generation, to the energy, then we see here we assume 550 terawatt hours, and we have already a part of 40% made out of renewables. How is this one split up? Here we have the details for the capacity, and you see, so hydro, biomass, wind, and PV, so solar called here, and we have the coals coming on here, and then the gas. This is how it is split up, and you see we have more than 60 gigawatt wind already installed. We have up to 60 gigawatt PV installed, but we want to have 200, keep in mind that one. And out of the 64 gigawatt of wind, we have not more than 8 gigawatt for offshore, and we wanted to have 30. And this is where we have to be faster. And now check how the picture changes if we go to the energy. Of course it changes because our power plants, our coal-fired plants, we can use more or longer within the year than we can have it with the wind or with the PV. And you see the reduction here from the PV, which gets a smaller number because we only have 1,000 hours per year. And the same we see here with the wind. We can discuss biomass, we can discuss hydropower, but the potential in Germany is not there. The numbers will stay like they are at the moment. Now, what does that mean for the electrical network? Now come a little bit closer to the transmission and distribution. We have new generation within the network, and we have distributed generation. This means we have it on the roofs, we have it somewhere in rural areas, but we do not have it there where we had it before. We do not have it in the area where we have coal, for example. But we have on the same side, we have off-consumer generation, so we have big wind energy, wind farms, which we have offshore. And we also have hydropower, not our hydropower, but with our neighbors. So they are still there. And this argument is always needed if some people believe that we can have everything locally within a small area, everything is distributed. This is not true. We also need our highways where we spoke about. We need the transmission network. But also how we have our generation is different. We have fluctuating generation, volatile generation, and we need a weather forecast. So our generation depends on the weather forecast, and these are no good news because you probably believe in weather forecasts, I do not really, and therefore we have here an inaccuracy which we have to deal with every second. And we have a new generation units. Our synchronous machines, so the typical type of machine which are now within our coal-fired plants, will disappear, and we get something which is made with power electronics. Power electronics is a perfect technology. Everything is possible with power electronics, but you have to learn those systems, and this is not as easy as it could be. So this is one of the very big research topics, how we can have a stable network with all these power electronic units. So we have a change in the generation. Why is it a big challenge? That's what we need. You see here a scale, an engineer's drawing, so just believe it is a scale. And if we have a balance between generation and consumption, only then we have our frequency stable with 50 hertz. As soon as we have more generation in every second, then we will get an increase in frequency. And this is not what we can deal with. We need a stable, a constant frequency of 50 hertz. So you see the wind, you see the PV. That what we have to do is to have a balance between generation and consumptions. Where are possible solutions? You see them here. You see the nice picture of the new energy world, and of course that what we have to do is we need a flexible power plant operation. So the power plants which are still in the network, they have to be more flexible, because we have now change within the consumption, change in the generation, and they have to follow, because at first our renewables are allowed to feed into the network. So the existing power plants have to be more stable, more flexible. That what we also need is what happens if the wind is blowing and the sun is shining and we cannot use the energy. We could switch them off, but this is not what we built them for. So we want to store the energy in different energy systems. For examples, here you just see very general power to X. X can stand for everything. X can stand for heat. X can stand for gas, and, or it just stands for the battery, which we can use. But please keep in mind, we will not save our network with batteries. This is not what we can do. We need more of these storages or these different energy systems. So flexibility within the consumption, so storage. Smart technologies, we can have brain or we can have our network just extended. But then we need a copper plate because we have a more flexible operation, because we have power flows coming from the bottom up to the top. That's what we did not have within the past. So smart technologies just to enable the current flowing in all directions. And of course, we need the electrical network which, with a copper plate, more than a copper plate, because we have to serve different directions. But also, let's see what happens within the distribution net or what happens within the transmission grid. Transmission are our voltages when we have more than 220 kV, and distribution grid is coming up to 110 kV. Here we can split up into rural areas and urban areas. Why can we do that? You cannot build a wind turbine within the city. So there we have different problems compared to the rural areas where you have these big roofs where you can install PV. What happens with the transmission grid? With that we already solved. We already said that we need a highway. We need a highway to bring the power from the northern part of Germany to the middle or to the south. So transmission with low losses over long distances. This is our task. And please keep in mind, in the past we had the big or large generating units. They are not there anymore. We have to operate the network without those power plants, which is a challenge. For us, we can say, and that you already saw, that without those large generating units, our network gets weaker, and an expert would say less voltage stable. So we have problems to stay with a constant voltage, and it is faster, and we have it less frequency stable, because the change in frequency, if we have a mismatch between generation and consumption, is just faster because our inertia is missing. Our big power plants are missing. So this is our challenge. Let's see what happens within Germany. You see here Germany indicating the offshore wind power here in the north, and you see the highways which are indicated here. The consumption more in the south, and this is exactly the reason for those long transmission lines. But in the background in blue, you already see, you recognize that there is a gas infrastructure which could help in the future. So that's what we have to do within Germany. We are not the sunniest state here within Europe. We have to use the renewables wherever they are. So the sun at the moment more in the southern part and the wind more in the northern part. Our major concern is how does this network stay stable, especially if you talk about system splits. Probably you recognized last year that the European network was split into several parts. Oh, sorry, into 2 parts. So that what we had is a big load flow, which was the cause for a system split. So the system was just broken with this line. And just imagine what happens if we have a windy day. We have wind here in the north and we have consumption in the south. If the network is really split in the middle, we do not have any chance that both networks stay stable. At the moment, it is guaranteed that it works like this, that every partial network can stay stable. So this is one of the biggest tasks which we have at the moment. But we do not want to complain because we have new tools that what we can use. We can change our network operation. We can change our network planning. Because probably if we have power electronics, which is very fast, probably we can use it to just get in action when a fault happens and not just in advance within the planning stage. So this is, of course, something which we could have, and we call this curative measures. So just do something if something happens within the network and not before. And then we probably can have less network which we need. The optimized grid operation should be a normal thing for us. So that what I already said, that what we do not lose on the way from the generation to the customer is nothing which we have to produce. So you see here within the title, hybrid AC-DC transmission grid. This is something very new. Hybrid for us means that we have the combination between our normal AC network and those DC transmission grids. And our research deals exactly with those transmissions and just what happens if we have more of those DC circuits here within our network and we have an overlay network. What happens now within the distribution grid? That what you recognize from your homes. Start with a rural area. That what happens, rural, we already mentioned, we have wind, we have PV, we can install, we have renewables all everywhere. The normal way would be that we have power plants here within our top voltage levels and they feed those networks and this from both sides. Now it changes. We have the renewable energies here at this part and we call it all for one and one for all. And what happens with this wind power if this city, for example, does not need the wind? We can feed it back to the high voltage level, but this is not what we call efficient. So we intend to have those wind farms used with more than just one network, which is new. This was not done before, so we have to change the principle of the network. And if you change the principle of a network, that what you have to do first is to check for the network protection. So what happens if a fault occurs? Can you recognize that fault and then can you split it out of the network, switch it off? We need innovative technology, so this is not that what we have at the moment, and here you see is indicated again that what we said, those converters where we go from AC to DC and backwards. But this is within the medium voltage network, not within the high voltage network. So we think about new principles that we really can have a combination so that we can operate those networks in a different way. Now go into the city. What is their aspect? If you look into the cities, then of course the electrical cars, they come around now. We have the cars and we have a different concept for heat because here again we have a current now feeding the heat. And this is what is the new challenge for those cities. And you see we bring together all those energy systems. So this is what we couple, the sector coupling which is going on. So that we do not just plan our electricity network, but together with the heating network and together with the electricity, with the transport system. And this sentence, this is what is really characteristic for my research. We know that we need central solutions, but we need them as central as necessary, as decentral as possible. So what you can do within your own city, please do it within your own city, but if you need energy from another place, then of course you have to transmit. We cannot avoid transmission. We talk about heat pumps, electric charging points, and we need to be flexible. We need something with an energy management because otherwise we have to erect everything in copper. We can do, then you have a big, big network, but this should not be the goal. So here now the research focus, we learned about the distribution networks with large number of decentralized generation plants, large number of operating states because the wind is blowing, you have a wind turbine over there, a PV installation on the other side. And at the moment we have one criteria which is always limiting the integration of decentral energy generation. And what is the limiting factor? It is the voltage, because we see the voltage is going up, so we need solutions, because if you can solve the voltage problem, then you have more renewables within the network without building new network lines. And that, of course, is a good idea. On the right side, you see the transmission grid, and we saw the highway, which we need. We have long distances within Germany. We want to use the grid, and we need a large number, increased number of redispatch measures. What is redispatch? Redispatch just said that you have your plan today, which power plants will operate tomorrow. But if something comes different as you thought about, for example, the wind is blowing more heavily than you expected, then you have to change that one. And then you probably have a line which cannot transmit more electrical power, and then you have to change the power plants which operate. This is very expensive, because you have to pay the power plant which is not feeding in, and you have to pay the other one which additionally has to feed. And that, of course, we have to avoid. We need the management without large power plants that we already had, that the power plants are missing in that, on that voltage level. What are we doing? We take innovative network devices, we have the change generation structure, and we model. We model those networks to guarantee stability, to have the network operated, and this means it is not just that they feed their power in. We need, for example, someone who takes care of the voltage, of the frequency. Someone has to do it, and this we call system services. We have to give the network operator new planning criteria, and the grid protection I already mentioned. So how to build a new network? If, for example, there will be a new place where people want to live, how big are those lines? How big are those cables? And we have to take care about the power quality, which means for us, in the normal case, voltage quality. So because we get rid of all those linear consumers, we have power electronics with a lot of harmonics. But I know this is very technical, but we have to take care, and we will do. You see two projects, and this will be the end of my talk. And you see here the one I already spoke about. This is financed by the federal ministry, and here we have, together with some other universities, that we really investigate this overlay network, and we investigate how can we have this one in a meshed system so that we really have more than just these point-to-point transmissions. How can we enable here, for example, rotor angle stability, so that we really have a defined behavior between the voltages in the north and in the south. Yeah. On the other side, we have our projects dealing with the distribution network there, where we have two projects. One is Delta, Real Labor project, and here we have Grid for Regio. This is another one. Here we really want to find out the optimum for the topology of a medium voltage network, and within Delta we want to find out, do we have a quarter solution? So how do we have to build quarter that we really can say that we are as local as possible? And this is what we want to have with storages and consumers and generation. That's it from my side. This is just the last slide where we just have a short view on the sector coupling. You see here the electricity sector, we see the heating sector, transport, and the gas production. And that what we here within our electricity sector did within the past is that we just built our network. But now we see that we have connections to all the other sectors, especially, of course, to the transport sector there where we have our electrical cars, but also the heating sector. So we want to get rid of the electrical energy, and then we hope that we can put it into heat, because then we can use it and we do not have to switch it off, because this cannot be the same. And in the future, of course, the coupling to the gas sector has to come, and this is where our plans are, where we think this could be the solution that we really can get rid of those big, long phases within a year where we do not have enough energy. But I know that Andreas will exactly take his talk about this, this section which I mentioned here. That's it. What is my goal? What you should take with you? Please take with you that if we change our generation sector, this is more than just going from conventional and central to regenerative, so renewable or decentral units. This is not what we do. We change the principle, and that we always call it, we have a paradigm shift within the network. It is totally new what we will get in the future. That's it from my side. Thank you very much for the attention.
Okay, yeah, thank you very much. Are there any questions? Yes, there are. Thank you. So please wait for the microphone.
Okay. Is this okay or not? I have to switch it on. So.
It's perhaps on.
Is it switched? Yeah, it is. Just for myself, take-home message for me, I somehow was surprised by this direct current, alternating current conversion. So what is the problem with this high voltage alternating current? There are these 400 kilovolt transmission. So there are some big losses, or what is why you need to convert it?
We will get a problem with stability, and we can start with the losses. So that what you have within the AC transmission, you need to feed your electrical field and your magnetic fields. And this, therefore, you need current for doing this. And the longer the transmission line is, the more you need for the magnetic field. And this, of course, causes a current, and the current has to be transmitted. And if you transmit the current, you have your losses. But this is just, okay, then we have some more losses, but it is less expensive than building a new HVDC. But that what you also have, that the voltages at the beginning and at the end, they are not so synchron anymore. They will run from each other. And this is what we call voltage stability problems. So you really run in a stability problem which you cannot manage, because you cannot say, okay, you bring them back together. They have to have a certain relation. And if you lose that one, then you have not the blackout, but you will lose the line. So therefore, you have a limitation for the AC transmission. Somehow clear?
Okay, thank you.
Jan Konvalinka, Prague. Great talk, thank you very much. It could not escape my attention, and I always feel funny if I see it on your map of Germany. My country is inside, in a way. You know, Czechia is like southern Saxony or eastern Bavaria. In your plans for new grid system, do you also talk to your Czech colleagues whether or not grids in Czechia will be involved, or I mean both on the research base or in the practical terms of the thing?
Yeah, thank you very much. Yes, of course, you're right. We do not have a German network because it is a European network, and you know that it is interconnected, so we cannot say that what we do does not affect Czech at all. So it is different. And of course, there are European plannings, but of course we want to be the first. So we do not want to wait, so we want really to have our goals and just to settle them. And that what you say, we had a short discussion during lunch. Of course, if you stay with your nuclear power plant, then you do a lot for the stability of the network, for the European network. But this should not be the German goal, just to rely on others, that they fix the network problems and we have green energy. This is not the solution. So it has to be one common solution, of course. Yeah, and we can also go up to Northern Africa, because if you probably know the old idea of Desertec. And if we talk about renewables, then of course we should go there where we really have sun shining. And this is not just Germany. and therefore we should interconnect those systems and use it wherever it is. Yeah. Thank you for the question. That's right.
Thank you very much. This was a wonderful seminar. And I have a question similar to that of Dr. Konvalinka, but broader, not only Czechia and Germany, but other countries, and especially Switzerland, since admittedly, I am from Switzerland, and we look down upon Germany that they had 15 years ago some good programs, and then came political pressure, also coming from Angela Merkel, whom I highly admire, but in this particular case, I guess that she put back German plans for modernization of electrification decades back. So now I would like that you tell us, at least in few sentences, which part of that what you told us is only that portion which is bringing you back to the level which you have lost, and which ones is really innovative and new, such that Switzerland could look in straight eyes with you.
You mean which technology efforts or which new goals which we have?
Pardon?
You mean new technologies, or do you mean new goals which we settled?
It is both. It is the fact that that Switzerland, the Alps have a lot of water. There, the emphasis is not so much on production and consumption. Your graphical representation is wonderful, but in the Swiss one would have a different production, storage, consumption. The 50 hertz would be of less importance because it would go through an intermediate stage of storage. So much more much more discussion goes into storage of energy, including the fact that modern cars with electric cars have batteries, and these batteries should be worldwide, not Europe-wide, connected, so that during the night they should be loaded, and all these fantasy things which looks fantastic, but if you listen to Mr. Musk, you see that they are way ahead of that what we are here thinking in Europe.
So that what is new for me, which came after the last election, is that we really put numbers on our goals. Because you remember the first slide, we have to be fast. That since I study electrical engineering, we have to be fast. That is nothing new. But to put here those numbers are so high that probably they are not will not be realized, but there are numbers, and this is now new. So these are the goals which now really have been identified and which really put a new discussion. This you can feel. So these are the goals. What is technically different? Of course, if you live in Switzerland and you have a country which is really in Central Europe, you manage the electricity, you have your GPS systems, you control the Turkey, you control from Turkey up to Spain, and then you see what is the behavior of the voltages. So this is your technology which you have there, which is fantastic and which helps you have a central role there within the network. This is clear. Where is now our new aspect? I would say that what goes in Germany into the energy management and in the energy consumption. I have one slide which I haven't shown, because that what will happen and what is discussed nowadays is that we change industrial processes. We have, for example, BASF, and they say we change it. We want to have an electrified process, and this is totally new. And that what is the consequence out of it is that we will not save electricity, as we indicated here. We will have more or the need for more electricity. But then we have new processes which are also in the right direction for being climate neutral, because we cannot just check for our electrical systems. We have to look into other sectors. And I would say this is a good step which we already made, but of course only a first. But you can imagine what happens if you look for industries, just ask, or if you have asked them 10 years ago, where can you save energy? Then they say, oh yeah, we can exchange this overhead line, and say, yeah, exactly. And this is different now. And this you can really feel, and this I would say, and the energy management. So this brain instead of copper. That of course, you can always build new overhead lines, you can build new cables, and then you can transmit, distribute everything, but you have a management, and if you have a management, then you want to use the electricity wherever it is, and then, for example, store it and so on. And the uses of storage, for example, this is where we hopefully have a step forward. You're welcome.
Frau Professor, I have been very impressed by the ambitious system of energy system transformation in Germany. So please don't feel offended if I introduce some questions that have not been answered by your talk. And that is, of course, I understand that the main purpose of the whole transformation has two targets. One, to increase the efficiency of energy use in the German energy consumption system. And the second one is to reduce the carbon footprint of the energy system. And I wonder whether you have also included in your considerations and calculations, setting all financial aspects aside, the energy and carbon audit of the manufacture, maintenance, construction, transport, and so on of the new energy fixing units, such as the solar panels and the wind propellers and so on, and also of biomass, which, in my opinion, for instance, the use of biomass has very detrimental environmental consequences. And so I'm not a physicist, I'm an ecologist who is interested in ecological energetics, and thus I'm also interested in alternative energy resources. And I was a great enthusiast for them in the 90s, but my enthusiasm has faded out a little bit after having considered the other environmental consequences of the introduction of alternative energy resources, like, for instance, wood biomass from forests and so on. So, but here we are talking mainly about wind and solar energy. So here my question concerns the energy audit of the construction of these new energy yielding units and the carbon budget, whether the carbon footprint is not being transported in a way a little bit aside from Germany to other countries where these systems are being manufactured. Thank you.
I know that, of course, this gray energy, it is taken care about, but I'm quite sure it will not be as much as you would like to see. We have to be honest. That what now is new, and probably this I can add for the other question which we had, is that we more and more talk about the circular technology, so that we want to avoid waste of energy, waste of material. This is then, of course, new, but I know that this does not really answer your questions. I have to say I'm not really aware. I know that a lot of people are calculating those big energy systems. I think they are somehow restricted to that what we have here within Germany, but I cannot really say whether whether there are persons that are doing that, what you asked for. Sorry. Yeah.
There was last question, I guess. So please.
Yeah, thank you for the very nice overview. A question came up to me, maybe it's an old question, but I think it's new, that is a smart spending of energy, that you can force both industry and especially households to charge, let's say, the electric car or the washing machine, if that is possible, let it run overnight and so on. So how do you see the potential of that, and what kind of infrastructure would be needed in order to control that?
Yeah. We always talk about the smart networks, but to be honest, a low network at the moment is not smart at all. It does not have any measurement units, you cannot control it, and therefore it is a big, big way up to that what we need for the management. That what we should do is to have some intelligence within the measurement, because otherwise we cannot finance to have measurement units everywhere. So there we need some clever solutions, and then I'm quite sure we will manage to have an energy management, for example, for the cars. But to be honest, I think this will not be enough. This will not save our networks. Why? Because now we have those heat pumps, and heat pumps, you cannot shift them. When it is cold, then it is cold everywhere, and they will have it all at the same time. And then we have to find for a different solution. So so for the cars, I think it's okay. We can have management so that we save overhead lines and cables, because this is always what we intend to do, that we do not have to have so much new networks, so much new cables, so many new cables and so on, so that we can manage. But here we heard about, we have the charging and discharging of the cars. This way is very, very long. So because at the moment we only have one direction, to charge cars and not to discharge cars when we need it for the network. So this step is very, very wide. And we, of course, at the moment we have always the conditions. So if you see households which erect now their own battery and they have storage, then they do it not for the network, but to earn money. And this normally is the opposite direction. So that does not mean that we save some cables, but it means that we need more cables, because this is a different management. So management, we have a chance, but we have to be more flexible. And as mentioned before, for the cars, yeah, there will be a solution. For the households, I do not think that will be the first way. So if someone talks about the washing machine, this is not what I would like to talk about.
Thank you very much, Professor Hansen. So we can proceed. So we know that the transformation of our energy system is something that has to be done. We know that we have to cut the emissions. So we know the target, but there are different ways how to reach these goals and what possibilities we have. This is going to be a topic for our next speaker. Let me introduce him. It's Professor Andreas Dreisler, also from Darmstadt University of Technology. Please welcome.
So, thank you very much for these kind words. Thanks for the invitation, Mr. President. Yeah, ladies and gentlemen, it's an honor to be here and talk about some aspects of thermochemical energy carriers that can be carbon neutral and are, as I show, important or can be of high importance for the transformation of our energy system. There are actually two topics I would like to cover. The first is I would like to discuss that chemical energy carriers are one possibility to store energy from renewable sources. That's the first part. And in the second part is a little bit out-of-box thinking, a new idea, to make use of iron as an energy carrier that can be used later on for CO2-free combustion. Okay. So the background, we heard about that. I think it's quite clear. It is that we need sustainability of our energy conversion processes. This is, yeah, a very important task, reflected by the Sustainable Development Goals of the United Nations. You see here goal number 7. It's about clean energy. It's goal number 7. It's about industry, innovation, infrastructure, about climate action, but as well partnerships worldwide. It's reflected as well by the European Green Deal. It's reflected as well by European, as well German and national hydrogen strategies. Looking at the challenges, transforming the energy system means, as we have just heard, about all sectors: electricity, heat, mobility, industry, buildings. And sorry for taking again Germany as an example. There is where I have the numbers for. In 2020, we contributed roughly 740 million tons of CO2 equivalents, corresponding to a little less than 2.2% worldwide. It's about the task to substitute fossil fuels by renewable sources. I think this is mostly accepted. Looking at the CO2 emissions in million tons over the last 60 years, sorry, you see a monotonic increase. It's only here where, due to the pandemic, we have seen a slight decrease, but we can be sure that it will, in 2021 again, recover at least partly. To reach the targets that have been set by the Paris Climate Agreement, we have to reduce significantly to reach the 1.5 degree Celsius target. The other one as well quite ambitious. In addition, at least for our country, as you have heard, we phase out of nuclear energy, and the plan is to phase out from coal as well. So we have to act now. I just repeat what Jutta said, but from my perspective, it's not clear which pathway is the best. Meaning that if you do not know exactly which action is the best one, it might be different for different countries. There is the risk for wrong decisions. And so from my perspective, we need technology options, and for the decision, for the choice, we discussed that, we need the entire life cycle, the carbon footprint to be considered. LCA is here, I think, a very, very important aspect and needs to be developed much further. I would like to focus here on the power generation to follow up what Jutta was talking about and giving some more background information about volatility. So looking back 2 years, we needed 545 terawatt hours. I think Jutta, very similar numbers, maybe not exactly the same. And looking at, let's say, hydropower stations, taking the largest one in Germany, that would correspond to more than 80,000 hydropower stations, to give you an idea about it. We look here at the capacity profile over the December 2019, I've taken those numbers, and we again see that in the peak we need 80 gigawatt. We see that we have a constant contribution by hydropower, biomass, which cannot be easily expanded. We see nuclear here in red, which will be faded out end of the year. We see on the other side, maybe difficult in this perspective or projection, these are here these small yellowish areas. This is due to PV, because it was December, not too much produced in Central Europe. And the remaining part, we see in greenish color here, wind. And then the remaining part is from fossil fuels, lignite, black coal, but as well gas, as we know from sources we have to get, we have to change. There are some times, like this day, for example, where wind was quite good, significant, but we see here a short dark period around Christmas where almost no renewable energy was available. So looking at that, for the moment we have an energy mix, fossil, nuclear, hydro, wind and solar. We already have heard as well from Jutta that integral values for renewable energies are between 40 and 50%. But of course, if you look at a certain instant, it is down to a few percent only. In the future, as we have seen, we need a massive installation of PV and wind, but still the challenge remains. They are volatile, as we have seen here. So we have to compensate for this volatility. The volatility, we have seen these numbers as well. Full load hours, PV, below 1,000, wind onshore, 1,600, lignite, for example, conventional central power station, much longer. To give you here as well the temporal fluctuations, you see the production rate of wind and solar over the year 2019. Maybe we just take only the mean value, which is the dark blue one, and you see here, for example, we provide here, you can say, in the order of 20 gigawatt, which means, as we already have installed in the order of 120 gigawatts, the installed capacity must be much larger than the required capacity. And looking at the future, depending on the scenario, depending on electromobility and so on, the numbers are up to 600 gigawatts. You have read in certain scenarios from DINA studies, for example. And that means a factor of 5. A factor of 5. I would say it's more or less impossible to get those systems installed in Central Europe. And so what we need, from my perspective at least, storage and transport of energies that came from renewable sources, but not necessarily from Central Europe. And looking at the possibilities, how we can store energy, you see here a chart how you can classify that, for example, is done using here the storage capacity, which is from kilowatt hour to a terawatt hour, so a logarithmic scale. You see here as well in a nonlinear scale from milliseconds to year, the so-called withdrawal rate. That is the time you can extract energy at a power level of that specific energy storage, meaning that, for example, using electrical energy storage. Typically, this is in the order of a few kilowatt hours and in seconds. If you go for mechanical storage, flywheels, for example, a little larger, you can do that maybe a couple of minutes. Electrochemically, like the lithium-ion battery, you can do that with several megawatt hours and maybe hours, maybe days. But if you want to go really to high energy levels at long withdrawal rates, there is only the possibility to go for power to gas. Power from renewable sources and gas, for example, hydrogen. But before we come to that, have a look up here. This is the annual demand you need, for example, for a large city. 3.5 million is here as an example. These are several terawatt hours. This cannot be done by the other ways of storing energy. So that's why chemical energy carriers is the only possibility providing large capacities at large withdrawal rates. And that is why people are so excited about hydrogen. Hydrogen is not so easy to transport. In principle, you can do so, but with some losses. That's why we should not only look at hydrogen. I think we should look as well as other carriers of renewable energies that could be green ammonia. It could be metals, like iron. And those are transportable and storable, and they can be imported maybe from MENA region, is the Middle East and North Africa, where by partnerships you have to build up. Maybe we can import energy as we do now. Yeah, and then, of course, once shipped to Central Europe, you can use them to generate power, you can use to generate heat and for transport. And so, the take-home message from this chart is chemical energy carriers are best suited for storing energy, at least at large quantities. Now, if you take these chemical energy carriers to store renewable energies, you can distinguish them further. One possibility is to take, for example, synthetic natural gas, meaning that contains C atoms, or liquid fuels as well synthesized using or make use of renewable energies like methanol or oxymethylene ether, which is a surrogate for diesel fuel. To make them really CO2 free, you have to extract the CO2 from the atmosphere, because afterwards, after use it in engines or in fuel cells, doesn't matter, you will release again the CO2. To have a closed circle, the atmosphere is part of the thermodynamic system. And that is not coming for free. Looking at different studies, you find numbers between 20 cents to 50 cents per liter, or 100 to 200 euro per ton emitted CO2 equivalent. That's one possibility. The other one, you can go carbon-free, and we just mentioned hydrogen, ammonia, maybe metals, semi-metals, non-metals. And then, because there is no C element involved at all, it can be CO2 free, and the atmosphere is not involved. Let's have a look into their properties, and I'll just take here one chart about it. It's the energy density, that's the energy per volume here per liter, or the specific energy on this axis, the energy per mass here per kilogram. To give you some orientation, the fossil fuels, diesel, gasoline, LNG, they're at this location. comparing them to hydrogen. You find liquid hydrogen at minus 253, I'm not sure anymore, degrees Celsius, or H2 compressed to 700 bar. They are very good in the specific energy as long as you don't take into account the tank. Yeah? If you have the storage tank for compressed hydrogen, it brings you back to the left, depending on the technology, of course. But if you take the property of the chemical energy carrier on its own, specific energy high, but the energy density low. Meaning for long distance transport by ships, for example, not very good because the volume matters. Here, ammonia is a better way. So if you want to ship instead of hydrogen the ammonia, it becomes better. But we should think about metals. Metals like aluminium do have a high potential because of their high energy density and high specific energy. I will later on talk about iron, and I will explain later on why. So you see different properties, and that, of course, comes along with usage in different sectors as well. So coming to the conversion, we have, once you have the chemical energy carrier, two possibilities to convert it back to electricity or mechanical energy, which is done by redox reactions. You can do that by thermochemical pathways, or more popular word maybe combustion, although many people don't like to hear that anymore, at least where I come from, or electrochemically, which has a better press, I would say, which is a fuel cell. Yeah, fuel cell here, combustion to the left-hand side, could be IC engine, could be a gas turbine, could be an industrial fire. But they are very different. And one difference is the power density. Thermochemically, this is a convection-controlled problem or system that scales with the volume, and we can operate systems up to the gigawatt scale. That is different in electrochemistry because it's very often, or typically catalytically assisted. It is diffusion controlled and scales with the surface and is limited right now to the megawatt scale. So orders of magnitudes of difference, and that needs to be considered. So having an interim conclusion, so what I've said is that chemical energy carriers are needed to store energy from renewable sources, and it depends on the application, whether electrochemical conversion or thermochemical energy conversion is better. You cannot say one or the other, because once you need the higher power densities, you need thermochemical pathways, meaning combustion technologies, that will be part of the solution. That's my strong belief. As I've said, that combustion technologies just fueled with hydrogen, for example, will be CO2 free. If you use synthetic natural gas, for example, they are at least CO2 neutral. But those combustion technologies, they do not exist now commercially. For example, people talk about hydrogen, but there is not yet any commercial gas turbine that can be operated with 100% hydrogen. Doesn't exist yet. Needs to be developed in a timely manner. And that brings me to the second part of my talk. There are no technology options to make use of hydrogen, of ammonia. I will talk about why this is typically as well used in connection with hydrogen, or has to be used in connection with hydrogen. But most of the time, the remaining time I have, I will spend on using iron particles. So we start with hydrogen. There are, of course, different ways, and all of you know about the fuel cell, but there are as well other ways. They provide as well a very high thermodynamic efficiency, and almost no one knows about it. And this idea is not actually very new. It already exists for some years. And this is the argon hydrogen engine. It can be used for stationary power, heat generation. And the potential is thermodynamic efficiencies up to 80% if you take a compression ratio of 20. And the idea is the following, that you take hydrogen that has been produced from green energies, and then you drive the engine cycle with argon. Argon has no rotational and vibrational degrees of freedom, and you have not these compression losses. And then you inject hydrogen and oxygen, and you burn it with very high efficiency, thermodynamic efficiency. You receive then water and argon has to be separated from the water, and argon is then kept in a circle. This is why you can do it only stationary. Another possibility is to make use of ammonia. I talked about, it's better to be transported, and it is a mass product already now, but it's not from green sources so far, but should be in future. If you burn ammonia, it has very peculiar combustion properties, and that's, by the way, the research I'm doing. Yeah, I'm a combustion specialist, and this is very excited about it, because if you now add hydrogen, you can turn it to be a very nice fuel, but still a lot of research is needed to make it clean in combustion because of NOx, for example. But the idea is that you then operate a large-scale ammonia engine where the hydrogen is produced on board, for example, on a ship. And big companies like MAN, they currently develop these kind of engines because you have the option for CO2-free long-distance transport, but it's not only ships, you can do it as well on trucks. And the last idea is about the usage of iron in particles and build central power stations out of that, or making use of coal-fired power plants and convert them. We call that retrofitting. That's an idea, and you have to consider that currently more than 1,000 coal power plants are built worldwide, and 2,000 or more are planned. And those are typically operated for decades, maybe 50, 60 years. And you need options to make them lower in their carbon footprint. And so this is what I would like to give some more ideas about it, and this is what I said, a little out of the box. It's a relatively new idea, and you see in the background the idea of using renewable energies in connection with central power stations that already exist, and make use of iron and its oxides and guide them in a circle. And this circle is shown over here. I guide you through. We start with the iron oxides. This is rust in particles, and this can be chemically reduced, making use of green hydrogen that has been, by electrolysis, generated from or produced from renewable electricity in fluidized bed reactors. That is one possibility. The other one is you dissolve it in an electrolyte and go the direct pathway using renewable electricity, and electrochemically you reduce the oxides back to elemental iron. Once you have done that, you put it, for example, on a ship. You take it from, I don't know where, Australia, from Morocco, wherever you have your partners, and ship it to Central Europe. And there, containing now the renewable electricity now in a chemical form. And then you burn it with the oxygen from air, again using fluidized bed reactors, or these are dust firing power plants. The most coal power plants in Germany are dust fired, where you have different diameters of particles. But this is maybe a detail we don't have to discuss over here. It's very important that after oxidation, you still have particles. Yeah? Meaning that you can separate them from the exhaust stream, and you can guide them in a circle, ideally. And by this oxidation reaction, by this combustion, of course, you create heat. Heat is used to drive a steam cycle, and then you operate a generator, and you again obtain electricity. And the efficiency, at least we estimate it, is in the order of 32–33%, 1/3. It's not so bad. It's comparable to the cycle if you would do it with hydrogen. A little worse, but not too bad. So that is the old idea. You burn the fuels to receive the thermal energy. And I would like to briefly outline why iron. Iron is oxidized, what we call in the type C. And this is shown here from the literature. I just go into this type C oxidation, where you see here the metal droplet. Why a droplet? Because of the high temperatures. It is melted, it is a drop. And you see here an instant where already some of the shell has been oxidized. So this black part is rust. It's porous, such that the oxygen can diffuse to that surface where you have heterogeneous oxidation reactions. And this is specific for iron because the adiabatic flame temperature is below the boiling temperature. And the vapor pressure of the resulting iron oxide is as well low. And only these two characteristics give rise to the fact that you have almost no loss of iron or iron oxides to the gas phase. And this is needed that you can keep it in a circle. Yeah? And that is why the iron oxides as particles can be removed from the exhaust gas by a cyclone or by a filter. So closing the iron circle is possible. And now the idea is to replace fossil fuels for high heat applications, meaning above 750 C. And that can be done for industrial heat, melting materials, for recycling. It could be done for chemical production, or it can be used in power plants that could be retrofitted to drive turbines. And this is where I have a few charts about a little more information. I show you here Niederaußem. This is a large coal power station in the west of Germany, operated by RWE. So the idea, at least we follow, is to have now an existing coal-fired power plant to be retrofitted and operated with iron particles. Still, we have to convince people that this is a good idea. We just started research on that. And then these power plants could be used as standby power plants in Germany to compensate for volatile renewables, but maybe in other countries we should not only look into Central Europe, but we should look as well in other countries where they currently build new coal power plants. Maybe their retrofit could be used as well for central power generation for normal operation. We think that using existing infrastructure might help for a better market entry. We have estimated, it's not me who done that, it was my colleague Johannes Janneke who did that recently, estimating the efficient potential, which is in the order of 46 to 48%, a little higher than hard coal, for example, because you don't have to remove SOx, because you don't have to mill the coal, and there are some other reasons why we have a little higher efficiency perspective. And then the iron cycle as well, I mentioned that already, has at least a comparable efficiency compared to hydrogen in connection with the gas turbine, which, by the way, as I said, not yet exists as well. We don't have any emissions of CO, soot and hydrocarbons because there's no C atom. We don't have any emissions of SOx because there's no sulfur, but there might be emission of nanoparticles and NOx. And that is currently actually only this bullet point where my own research is going on. Yeah? So we're looking into these interesting issues. However, from that perspective, at least, this could be a way to make use of existing infrastructure, and it is something that might be used as well in outside Europe. However, let's have now a case study. As I already said, we make use of this Niederaußem, this power plant you see here. A couple of years back, they produced 23 terawatt hours in the year 2018, and it was operated with lignite. And now we want to think about replacing that by firing with iron. And for that study, we assumed an efficiency of 40%. And then the requirement for iron powder would be 28 megaton per year. Let's assume that you can guide it in a circle 4 times a year. Yeah, after you have burned it, you collect the particles, the oxides, you bring it back maybe to Morocco, you chemically reduce it again and bring it back within 3 months. You do it 4 times a year. That means you need 7 megatons. Compare that to the steel production in Germany. 2 years back, that was a factor of 5, so 35 megatons per year. Ideally, you just need this iron once, because you would guide it in the circle all the time. But that's a dream, it's idealized. There is a certain loss rate for sure, but we don't know yet. It's needed to be researched. Let's have a look now how much hydrogen you would need from renewable sources for the chemical reduction, and you end up with 1.5 megaton hydrogen per year. And now assume that you have an electrolyzer which is operated by wind and PV, and this is operated for 4,000 hours per year, which is quite optimistic, I would say. Then you would need 25 gigawatt capacity just to get this amount of hydrogen which is needed to get the iron in the cycle. Let's have a look at the plants. I have a little different numbers, Jutta. I'm not sure where you have the 10 gigawatts from. At least from the hydrogen strategy, I read about 4 gigawatts in 2030 for Germany, and for the European Union, 40 gigawatts. And compare these now to these numbers, and you see that maybe with the European plants, if this number would be correct, you can replace 2 of these coal power plants. Yeah, independent whether you burn iron or hydrogen directly, that's the same magnitude, and you see that iron is not the showstopper. The showstopper is that we don't have the capacities of the electrolyzers, which, by the way, in another project I'm involved with, we currently develop to upscale them, because we don't talk about costs for the moment, but it will be extremely expensive to build up all these infrastructure. Maybe just in a graphical view, you have seen here the electrolyzer capacity, and here's the substitution of the electrical output of coal-fired power plants, and here was Niederaußem, 23 terawatt hours per year. If you now take all coal power plants in Germany, which was, I think, last year 130 terawatt hours, something like that. Compare that to that green line, which is the European plan for electrolyzers in 2030. You see, if you take again this 4,000 full load hours per year of the electrolyzer, there's a significant gap. So with that planning, although this is already quite ambitious, it is by far not sufficient. And so we need a massive installation here, not only of PV and wind, as well a massive installation of electrolyzers. And so we should be honest, this will be very expensive. I don't know numbers, sorry, but it will not come for free. And so this brings me to the summary. So the take-home message from my side are, chemical energy carriers are part of the solution. We need a worldwide trading of chemical energy carriers, because in other countries it is much cheaper to produce power from renewable sources. We not only will rely on electrochemical devices, my strong belief is we have to use as well thermochemical energy conversion technologies, because they complement each other. And both will be needed, and the other word for thermochemical energy conversion is combustion. And CO2-free combustion is doable, for example, by the iron cycle, with the potential for producing heat and electricity, but not for mobility. For mobility, hydrogen and ammonia are the better choices. And with that, I think we need quite some efforts to achieve the Paris targets in 28 years. I think in Germany we agreed as well upon that politically to do it 5 years earlier. And this can be done only when we have extensive research and development in energy science. And what we need as well, I think, is openness. We should not be fundamental and say only this option is the right one, because we do not know yet. And that is why my play is for openness to technology options. Thank you very much for your attention.
Thank you very much. And now it's time for your questions or your comments. So please wait for the microphone. Thank you.
So can you actually comment a little bit more on the upscale of the electrolysis capacity? Because it seems to me that this is the major part of the problem, that you really need a lot of hydrogen. The only way how to do it now with electrocatalysts based on precious metals, simply it won't work because of the lack of those metals. So what is the idea, or what is the plan for order of magnitude increase in the production of hydrogen, if any of those ideas actually have?
Thank you for the question. I expected a question like that, but you have to know I'm not a guy from electrochemistry. I'm from combustion. However, I'm involved in this project because of transport limitations people observe. And what I learned from them is that, for example, a zero-gap electrolysis system seems to be an option to increase the efficiency with less precious metals as well, using different kinds of electrode structures. So what I know about it is maybe not all the truth, but what one problem is actually the transport of the gas that is produced in the surface area that needs to be removed from the electrode structure. And currently we are looking into this transport limitation that comes from this multi-phase fluid problem that we currently look at. And what people as well are looking into different materials, but there might be other experts with more knowledge, and I would not like to comment on that because that's not my field. Yeah. So as I said, the transport limitation is one thing in large devices to optimize.
I have a related question because my feeling is that production of hydrogen by electrolysis of water is, from the thermodynamic point of view, one of the very inefficient, and there are much better ways how to produce hydrogen.
You mean from renewable sources?
From methane, for example, from other sources, but not from water.
Yes, possibly. I haven't looked into that, and I have no numbers that I can really comment on that. Actually, at least in the hydrogen strategies I have looked at, it is the electrolyzers that are preferred. But I'm not sure about the other options as well, with their scaling and things like that. And I'm not sure about as well the economic perspective.
Well, I understand that this is not your expertise and certainly not your responsibility, but still, given all the complications that you partly named, do you personally think that the phasing out of the nuclear power plants in 2022 is a smart idea? And maybe more generally, is there an ongoing discussion in Germany about this problem? Because I'm not following the German discussion very closely these days.
Yeah, first of all, what I think is very important to have technology openness. That's one thing, which is not, now you ask me personally and I have to answer personally. I think that the debate about energy in our country is not so open. It is strongly determined by sometimes wishes and some, how we call that, but it's some kind of fundamentalism sometimes, yeah, I would say. And I'm not sure whether it's a good idea or not to phase out, really. I think you have always pros and cons, and it was a political decision and a decision that has been taken by the society. And right now, despite the crisis that started 2 months ago, there is not a real debate about nuclear power, and not even about the plans to fade out from coal already in 2030. People not openly discuss it, at least. What is done politically behind, I don't know. But to be honest, I think right now there is a small likelihood that the plans for nuclear power, usage of nuclear power, will be changed this year. At least that's my perspective.
Thank you very much.
Yeah.
I will go back to your presentation. So why rely on iron? Because on the graph you showed, from all the elements, it was probably one of the worst, right? So why not focus on aluminum, for instance? That would make better sense.
Yeah, well, thank you for the question. Back to the talk. I feel more familiar with that. Aluminium is for sure as well a very interesting way, but it's called the so-called wet cycle. If you make use water, steam, pull it over the hydrogen, you get as well over the aluminium, you get out hydrogen and make use of maybe in gas turbines. We will look in future as well into that, but for the moment, saying when we want to retrofit existing coal power plants, it will be not possible with aluminium because it is not in this type C oxidation, which is dominated by heterogeneous surface reactions, and therefore you get it into the gas phase, and then you can't get it back. You want to have it in a circle. That means really the flame temperature must be low enough that the metal is not boiling. And that is not true for aluminium. And that is, therefore you would have loss into the gas phase. Maybe you have condensation as well to nanoparticles, but those are difficult to remove. To remove particles from the power plant, it must be in the dimensions of a few, ideally tens microns, to make it with cyclones energetically efficient. And that is why iron is preferred for that application. If you want to maybe do not make use of existing coal power plants for retrofitting, but transport the renewable energy, and in the end, again, want to produce hydrogen from it for mobility reasons maybe, then aluminum is the better choice. I totally agree.
And this is
different question, I don't know, not on the chemistry, but more on the nuclear fusion. I think that there were several projects, or there are projects on fusion of hydrogen. Well, Cadarache, for instance, in France, or I don't know, Dessy was also involved. I don't know how far is that, or I'm not familiar with progresses of these projects. Can you brief us?
So we have something in common. I'm not informed in detail as well, sorry. I have to say this the third time here. But what I heard is always fusion is close, which means it's 50 years. Actually, I do not know when it comes to be commercialized. So I think for our generation at least, it comes too late. However, what I strongly support is technology openness, and that means spend money into it and try your best.
Yes, I also always hear 50 years in future it will come. But still, it needs some financial supports, and maybe is Germany supporting these projects?
I think so, yes. I don't know the numbers by what, but it is financially supported, yes.
I'm a chemist, also actually electrochemist. The aluminum is the most expensive metal to be produced electrochemically by electrolysis, which means that you are investing electrons into converting aluminum oxide, bauxite, into aluminum metal. So just to give you an example, 1 can of Coca-Cola will be equivalent of burning a 100-watt bulb for several hours.
Mm-hmm. Yes, I understand, but maybe you can give us the numbers of the efficiency to turning power into aluminum back. Isn't that over 90%?
It doesn't matter. I mean, if you complete the Carnot cycle, you invest the energy into reducing aluminum oxide into metal, and then you convert metal into aluminum oxide. You cannot gain anything.
No, you can't gain, but the question is how much you lose. And the question, of course, is it better than, for example, using hydrogen, where most people are talking about, which is in the order of 30% efficiency. And that is, I think, with aluminium, I don't know what the cycle efficiency would be, but it's maybe as well similar order of magnitude.
Are there any other questions? Okay.
I have as a naive question. You said that one of the advantages of this technology of producing iron is that you can reduce it to iron, let's say, in the countries where the sunshine is abundant, let's say in Africa, and after that you transport iron to Europe. But what's the level of oxidation on the way? Because you will lose a lot, because you will produce rust on the ship.
Yeah,
Did you estimate this?
Thank you very much for the question. You have to consider that. It can be transported in big packs. You have to cover them, and like maybe you transport coffee, you have as well to put some inert gas like maybe nitrogen into that. We're not sure about it, how fast it will be, but it is an issue. Yeah, it is oxidizing, of course, on its own, and you have to prevent that by using big packs. But this is being done. There are commercial solutions, because iron powder is used in laser sintering, for example, and there they do it. If it comes to the costs, that's the question. Yeah, we don't have numbers on that, but it will be much more expensive than what we currently pay for a kilowatt hours in the production. That is for sure.
Okay, thank you very much. We can proceed. Thank you, Professor Andreas Dreisler. And now we can look at future energy systems from various perspectives. Let's look at some figures, scales, and rates. Our next speakers are Ondráž Přibyla and Jan Krčál, both from the project Facts on Climate Change.
Ještě druhý, kdybychom měli. Thank you very much.
Yes, debate.
If possible. So, ladies and gentlemen, good afternoon. It is an honor and also a surprise for us to be here. And surprise because, well, first, a week ago I didn't know that we will be speaking here. And the second reason is that we are not a research institution. We are a science communication group, which means we are not focused on research. We try to make sense of the research. And sense making for this talk, I mean, how do we make sense of the situation so we can act in it? During the last 2 years, during the COVID, we realized that it's not enough to have the research. The society needs to make sense and to make decisions that are relevant. So we are more focused on heuristics, on relevant simplifications, also on questions that are that should be focused, the attention should be focused on. And the data visualizations that should be self-evident, so people understand them, and that can help us guide through the transformation that is ahead of us. What kind of transformation is ahead of us? Well, we've seen several takes this afternoon. Here we can see that 87% of global CO2 emissions come today from states that promised carbon neutrality. That means in some 20, 30 or 40 years, we will need to overhaul the whole economy, the whole energy systems. And the basic strategy for this overhaul is twofold. First, electrify everything that is possible to electrify, and then produce cheap electricity. Carbon-free. Well, cheap and carbon-free electricity, yes. So we will need to focus on electricity, basically. And to give you an appetizer of data visualizations, here we can see how the consumption and partly also the energy mix changed in the world, in European Union, USA, China, India, and the rest of the world. You can see that the consumption is reasonably flat in EU and USA, is rapidly rising in China, India, and most of the rest of the world. You can also see what portion of the consumption is generated by, and this is electricity, this is not primary energy. What portion of the electricity is produced by fossil fuels, by nuclear, and by renewables? The question is this a relevant way to look at things? Because you see that all these graphs are of a similar size, while China and European Union are not of a similar size in terms of population. So we can plot not just the mix, so to say, but we can plot consumption per capita. And here you see completely different story. While European Union, well, consumption in European Union remains reasonably flat, USA too, you can see that USA consumes 2 times the electricity per capita than European Union. India is barely visible on that graph. Well, China starts to be visible and starts to be comparable with EU. I said that we will need to electrify everything, which means also in EU and USA, the consumption of electricity will go up. We will also need to think about energy mix. So I would like now to focus your attention on how we can think about energy mix.
Maybe, sorry, let me add one thing, because you said it will go up, but you didn't quantify it. And I think it's good to inject here a bit of an estimate. It's like rough, okay, worldwide, but also in the EU, maybe think of something like 2x. So increase by 100% of the consumption in 30 years from now. So like the size of the problem is now double in the sense of covering our electricity needs. Please go on.
Yeah, as a rough estimate. So how can we think about future electricity mix? Basically, there will be three pillars of any electricity mix: nuclear, fossil, and renewables. We can roughly say that the sum of nuclear, fossil, and renewables should be 100%, which gives you an equation of a plane, and basically the plane gives you a triangle. So this is just a play with geometry of the space. Okay, yeah. The triangle gives you a nice map, a very simplified map, but this map could be useful for people to think about the transition. If we want a society to go some way to the future, we need to have a way to use, to show the path. We need to have a map. And this works roughly as a good map. The limitation is there is no biomass in hydro. But this is up to 15%, so there is something...
at least for Czechia.
At least for Czech Republic. And the limitation is, in this picture, there is not the consumption rise or electrification. Fossil fuel is... The main advantage is it's dispatchable, but it produces greenhouse gases. So we need to go down to mix of nuclear, which is expensive, and renewables, which is currently reasonably cheap, but also intermittent, volatile. I try to... Yeah, I can point here. So the starting positions of European countries are different. France is mostly nuclear, has very little renewables and very little fossil. Czech Republic is somewhere between nuclear and fossil. Poland is mostly fossil and some renewables. Poland has no nuclear plants, as far as I know. Germany is starting here, but during this year it will go up to this point. And there is also Denmark, for example, which is roughly 50% between fossil fuels and renewables. So these are starting points. Where do we need to go, and what are the limitations of the path? Well, we can think about it as a chess game. I hope many of you play chess, so you know that there is a different strategy in opening, middle game, and end game. And we, as a same principle, we will have different strategy in the opening game, middle game, and end game for the energy transition. The opening game and middle game allows no nuclear power plants to be built, because it takes time to build a nuclear power plant.
And this is again the game of chess for Czechia, I mean game of electricity chess. So Germany has a completely different game and so on.
Yep. Yeah, and I started at this at the point at the starting point of Czechia. So we will basically we can either stay at the place, or we can start to move towards more renewables. And only in the end game, there starts to be some portfolio of changes. We can either choose a strategy to go 100% renewable, or stay partly nuclear, or go more towards the nuclear direction with advantages and disadvantages. The overall strategy for opening game and middle game is basically install as much renewables as we can. Because in Czechia, we have so little that it's barely worth mentioning.
When we speak about the game for the next 10 or 20 years, which is building up renewables, solar and wind, like there are two main obstacles that people speak about here in Czechia. One of them, maybe Czechia does not have the potential for enough renewables. And the second is, Well, but they are intermittent, so it doesn't work. You know, it doesn't work like old coal that just is stable in the production. So let's look at those one by one. When speaking about potential for renewables, I think the simple answer, when we look at the expected consumption, let's say 125 terawatt hours per year in 2050, I mean, this is a rough estimate, but as a ballpark, it is useful to have this perspective. We can cover all of this easily with solar. Like if you take like 1% of the land area to produce this amount of electricity using solar. And if you think about how much land we use for rapeseed to convert it to biodiesel, it's more than that. So if we are okay with growing rapeseed for biodiesel on some portion of the land, then like we can produce enough solar electricity using the same land area, even less. And obviously, if we are willing to spend more of the land area, we can even create more solar electricity in Czechia. As regards wind, it's more nuanced. So the potential is much bigger than what we currently produce in Czechia, like maybe 30x bigger. So maybe we can cover something like 10 or 20 terawatt hours per year with wind, maybe even a bit more. But it's limited. So we cannot, with current technology, create maybe 100 terawatt hours of electricity from wind in Czechia. So this is something we need to keep in mind. The second question, and now, sorry, a bit of technical interruption. Yeah, this is what I wanted to show you, is about the intermittency. So this is a graph of solar and wind production over the last year in Czechia, where the color represents the daily, like each stripe represents one day of the year. So the redder the color, the more solar electricity is generated. The darker, again, more wind electricity is generated. Yeah, no. I just was looking for the laser pointer. So what you can see here is, first of all, seasonal trends. Like, obviously, we create more solar electricity over spring and summer. We have a lot of variations over individual days. But just to quantify the variation, this has been mentioned before in one of the talks. So we need to quantify the difference between the minimum and the maximum for solar and for wind on this map. So, András, can you switch it? Thanks. And this is a sad story, because the difference between the minimum and the maximum, so the minimum is like 3% of the maximum. And this can happen at the same time. So if there is a bad day, this means we get like just a couple % of electricity from solar and wind in Czechia. So intermittency is a real problem and needs to be addressed. So we look quickly at 4 strategies, how we can address that. First of them is, well, weather is, the variation of weather gets evened out if you look at a larger area. So Czechia is a small country, so the weather is quite uniform in Czechia. Here you see the production from wind in the first 5 months of the last year, and you see how it hops like up down almost to 0. So the minimum value for a given day is like basically almost nothing. If you look at the wind in the whole European Union, then it also hops up and down, but you have this band of wind power you generate somewhere in Europe every single day in this time. And I mean, if you also look at larger period of time, you would see similar patterns. This basically calls for building up more and more interconnectors in a sense. Like it's hard to be self-sufficient with wind or with solar in a small region. Obviously, this is costly, as we've heard in the first presentation. Like building up interconnectors connecting the Europe more and more is costly and it takes years. But if we want to like minimize storage in a sense, or if we want to use a lot of the electricity we actually create, we just need to connect Europe better. The second point is obviously we need some short-term storage / backup. So if we look at the same graphs, but we put 7-day averages into the graph, you see the same story for Czechia and for Europe. And like the minimum value is now getting quite close to the average value that is produced over the year, which means if you can cover up a couple days of bad weather, then it starts to be more reliable in this sense. But short-term storage is complicated. What we need for a bad day in Czechia, we need something like 150 gigawatt hours. I mean, if you imagine you have something from nuclear, and then there is a bad day and you produce nothing from solar, you produce nothing from wind, then the rest of the consumption that you need to cover is like 150 gigawatt hours. And we are, with our current capacity, we are an order, almost 2 orders of magnitude far away from what we need. Like the pumped hydro, less than 4 gigawatt hours, batteries currently installed, negligible. Some of it can be dealt with dispatchable generation, but not all of it. And we currently would need coal or gas just to cover the missing electricity. In the future, you see that like if we really succeed in building so many electric cars, there will be a lot of capacity in their batteries. So this is just an estimate for having 5 million electric cars in Czechia by 2050. So you just see like you get to the same order of magnitude. Hopefully we will crack this. The third solution is actually a discussion about long-term storage. So as been discussed in the last lecture, we obviously need solutions for long-term storage, like hydrogen or iron or anything else that can be transported and so on. But the right mixture of solar and wind actually decreases the need for the long-term storage. This is, and luckily in Europe, we have a relatively good mixture of solar and wind. So these are weekly aggregates of production in the whole EU from wind. This is the summer dip of wind production. This is the summer dip of solar production. And if you put them together, you see it's actually relatively reliable in the point of view of weekly aggregates. And the fourth solution is obvious. We need a bit of overproduction. So if our demand is here, then this is not enough. But if our demand is here, so we kind of scale up the production so that even in the worst week, we have enough electricity, then we don't need so much of long-term storage. Yeah, bit of overproduction.
Now come hands-on and pictures, and this will be a bit tricky because we had a problem with technical problem with images and imaging and connecting the device to the projector. So we will try to do best while zooming on these pictures here.
So basically what I want to convey in the last part of the talk here is it's good to look at statistics and graphs, but like what gives the best insights is looking at the hourly production, like how does it look in real weeks of the last year. And we have like artificial plots. So this is the this is a master slide with a lot of detail. So this is Czechia now. This is a simplified version. Each row is 1 week of data from 2021. The thick line is the demand. Now, the gray color is nuclear. And then something very small that you can hardly see. Here you can see it better. This is wind and solar. So basically we see the current production of renewables in Czechia is almost invisible in this projection. So if we move to the right, if we imagine we multiply solar in Czechia by a factor of 4, and we multiply wind by a factor of 20. Sorry, what I forgot to mention, the dark blue is hydro production, the light blue is wind. I hope you can see it a bit. So if we multiply by this factor, which still is pretty much below the limits of what we can build in Czechia, then you can see, and this is kind of for the mid-game, if we build these capacities, you see that quite often these capacities eat up into the space that would otherwise be covered by coal or gas. So we can definitely build up enough in Czechia to reduce the need to use fossil, and we would use them in the midterm just to cover the areas in between the parts of the graph that is white now. And with this production, you can also see that in some of the weeks, some of the day when it's sunny, by the way, this is based still on 2021 data, so like the 4th of May was sunny, and this is what the plot shows. So in some of those days, you would see an overproduction. So there is some potential for storage, for storing electricity to batteries and so on. Ondráš, if you can move down. Now this is tricky, don't go, yeah, this was tricky, go back. You need to be careful so it does not jump. I've trained it before the talk, so let me try to do it. Sorry for the technical problems. So you see, this is not every week of the year. Some weeks are missing. Here you can see, this is these are the hours of the year. And this is the hours when carbon-free electricity is missing. So most of the hours of the year. Oh, and now we've lost it again. You try to change something. Anyway, and some hours of the year we would have surplus of electricity. So, I mean, you could have batteries that you would charge maybe 20% of the time. Let's move to the extreme case for Czechia. What's the time mark? That's good. So this would be even doubling again the production in Czechia. And as you can see, like now the excess electricity gets massive in some of the weeks. But still there are weeks, like this one, where you get almost nothing in some of the days. So this is again a call for, we need interconnectors. Like Czechia is so small, or we need a lot of, I mean, like both of the talks before gave you some solution. We need either really strong interconnectors to get electricity from somewhere else when the weather is good somewhere else, or we need good long-term storage to be able to create the electricity from other sources. Yeah, but this is, again, this is maybe on the edge of what we can get from wind. From solar, we can easily get so much. It's just a matter of years to build it up. Let's look at the next slide, which is Germany, because we've got some speakers from Germany. And by the way, in the previous graph, I kept the load the same, no matter how I scale up the production. So this did not respect the increase of consumption of electricity. This is Germany now. So you see, I mean, like they've done a good job in a sense that even today or in the last year, you see quite a lot of wind and solar generation. If you can move down to see maybe a couple more weeks. This is the summer, a lot of production from solar. This is winter, again, a lot of production from wind. But like barely ever, there was an overproduction in Germany in the last year, caused by shutting down a lot of nuclear in the past years. So like, I mean, if we go back a couple of years, we would see more overproduction, but like in the last year, there's very little. Let's look at the right part of the German graph, which is the plan of the government for 2030. roughly, I didn't distinguish offshore and onshore, so like it's simplified because these would have different capacity factors and like slightly different shape, different weather patterns. But you see, again, it's quite a lot of production, some weeks overproduction, some weeks not enough. But if we look at this week of February, that was also bad in Czechia. It's also bad in Germany. Germany is close to Czechia, in a sense. So even when Germany fulfills the very ambitious plan for 2030, there will be weeks in the year where there will be not enough electricity renewably, locally produced. I mean, I'm just stating the obvious, but like this allows it to see it graphically. Let's look at the extreme example, and this is the aggregate over the whole Europe, which is super simplified. Obviously, we cannot easily transfer all electricity from one part of Europe to any other part of Europe. So this is like an abstraction of perfect transmission of electricity. So EU, I think this is EU 28. Today, also visible amounts of electricity from solar and wind, but not truly covering the needs. This is not so important. Can you move to the right side? This is if we just double the production of solar and wind. I mean, it's a big feat, but if we double it, you see a lot of days we almost touch the demand line. And if we go even more extreme, which is 5x, we could then look at the points in between. Maybe 3x or 4x would be almost enough. If we multiply by a factor of 5, you see that rarely ever there is not enough electricity in the given hour in Europe. Maybe you can go down to see a bit more weeks. This is the summer, a lot of overproduction. This is the winter, again, a lot of overproduction from wind. And here you see the graph of shortage of electricity, which happens but rarely, and the surplus. So you would see that like 100 gigawatt of electricity happens to be of surplus electricity is 40% of the time. So you could build up hydrogen electrolyzers with this capacity. So this is 100, which is consistent with the number in the lecture before for Europe. Like, okay, the plan was like 30 gigawatts, I think, for Europe. So if we manage to build up so much, 100, then we would make use of them just 30% of the time. So we would get like utilization rate of 40%, which is good, but like very far from 100. Okay, let's summarize. Maybe you can, András, summarize the first part in a bit.
Okay, so what to take home from our I'm hesitant to call it a lecture. It's just
let's look together at the system and problems.
Yeah, presentation, looking together at the problems, yeah. So what to take home? Well, there will be different parts of the game, and the strategy for opening game and the middle game is quite clear. The end game will be difficult because of the intermittency of the solar and wind. And we can try to communicate this with a simple graphical map, so to say. And
there is room for growth for Czechia renewables. In order to grow, we definitely need governmental support, and which is kind of non-existent at the moment, to really build up. And we don't face the issues with intermittency for quite a bit if we build up more capacity. This is not the problem for this decade, that we don't know how we're gonna cover the missing bits.
And perhaps for the end game, in Europe, 5 times solar plus 5 times wind could be roughly enough.
I think if you look more at details, maybe 3.5 would be the right factor to increase. That would cover the needs. We would not have too much electricity for hydrogen for industry. So, yeah, in the result, maybe something like what you said. Yeah, we are open to questions.
Thank you for your attention.
Okay, Pavel Jungwirth has a question.
Actually, it's not a question, it's a word of explanation because you mentioned week before you didn't know you will be speaking here. This is absolutely true. We had a cancellation of a speaker, and I just thought András could fit in. I called him, and he did with his colleagues. I'm very happy you did it, and you had very little time, and I think you did a perfect job to present your project and put it in the context of today's lecture. So these guys are working on a webpage, faktaoklimatu.cz, and their work is really to communicate science. And I thought this is another aspect that is sometimes overlooked, and it's extremely important, and I'm very happy you did this job for us, and thank you very much.
Very welcome.
So, are there any questions? Yes, there are.
Thank you very much for your talk. And let me ask a question. Why did you postulate at the beginning of your talk the highest possible rate of electrification of the country or of the countries of the EU? Why didn't you include also direct use of heat from thermal pumps? Because any conversion of electricity to heat is actually energy degradation connected with a lot of entropy. So I'm just wondering whether it is really the most the wisest use of electricity just to create high quality energy in terms of HT-ODUM or X-energy, and then degrade it again to heat, which is the lowest form of energy. So I wonder, why did you not include in your energy mix thermal pumps, which really use only a small fraction of electricity for the moving the air or water or any other medium, and the rest is really direct transport of heat from one place to another? Thank you.
Thanks for the question. This is a good question. Obviously, we consider ambient heat, so we simplify things. When we say electrification, we mean using electricity for heating in terms of heat pumps. So obviously, if you look at the whole energy mix, ambient heat would be a big part of it. But in our simplification, we call it just electrification. Nobody proposes to use direct heaters, like electric heaters.
In science communication, we often need to simplify and to make a relevant simplification. So, because we wanted to focus on the intermittency problem, the other part, which is how much do we electrify, is probably simplified too much. And the main message here is the consumption will increase. Basically, by including the industrial processes and by including heat production, whether you produce it from the pumps or whether you use any other way of producing heat from electricity. So there will be increase of the consumption. That's the main message. And it would call for a more nuanced talk for this problem of how much do we electrify, how much the consumption will increase, whether there are ways to reduce the consumption to save energy. This would be whole complex universe of choices that we can make, and that's also hard to navigate. Then, does it answer your question?
Good afternoon. I will have short addendum, not have a question. We are sitting in the room where there are some curtains. It's not photovoltaic curtains, it's just for making it a little bit dark. And contemporarily, the light are switched on, And as I looked on the candles, I don't think those are some very modern candles. I think those are some halogen candles, as far as I can recognize it. But there are about 36 lighting candles, and both are curtains in on. I think that there is a lot of speculation and discussion if going nuclear or some sparing photovoltaic or wind energy. But sparing in the households, in companies, is a very important step. Somewhere was told, not very often, but even that lowering the room temperature about 1 grade means lowering 6% of the whole consumption. My question is, why it is not more communicated? Just lower the energy consumption on your side and just look around you?
And the answer will be provided by next speaker, as he is already signalizing to us.
Yeah, well, as you apparently collect data from different disciplines and present them, my question will be more general than probably the rest. So basically, everything was only focused on, let's say, how we can try to produce less CO2, and it seems that it will be very, very expensive, probably too slow. They will be not fast enough. So can you perhaps tell us a bit more whether there are some realistic efforts on the other side to try for sequestration of CO2, that, for instance, the most consumption of CO2 is in the ocean, and most parts of the ocean are basically dead. So basically, fertilizing some parts of the ocean may consume huge amounts of CO2. So are there any realistic plans to use this approach as well, or we will just cut down all the production of CO2 and hope that it will be fast enough?
Well, this is, again, a whole universe of complexity there. And so let me address a few things. One is we need to lower down the production. And realistically, carbon production, the production of greenhouse gases. Realistically, we can lower it to perhaps 1/10 or 1/20 by 2050. That could be basic estimate. And the rest of it, so if the total production rough estimate could be 50 gigatons a year of CO2 for today, then in 2050 we can have some 5 gigatons a year. And we need really to go down with the production of CO2. It's difficult to foresee what ways, what technology will allow us to reduce the last 5 gigatons. But given the price of a ton of CO2, which is currently around $100 per ton, it will, by the estimates, it will make 1% of GDP in 2050, almost, which is a huge sector. So basically, carbon capture and storage will be, no matter the technology we will use, will be one of the biggest sectors of economy, of the global economy in 2050, which is a huge change in 30 years. I am hesitant to say we will not need fertilization of ocean. I would be very careful with this, the playing with the planet in such a scale and playing with the natural cycles in such a scale. That's what I can say from that data perspective or from what I saw there.
Maybe I can add, thanks for the question, really important one. But we haven't picked the low-hanging fruits yet. So, I mean, first in this decade, we need to decarbonize as much as possible cheaply enough. And then we will see. It's hard to predict what happens in 10 years. But like, if we cut down the production to half or over longer time to maybe 1/3 of today, it's a less problem to solve, and it buys us more time to think about next solutions that might be cost effective.
I just wonder how much concentration of CO2 can be influenced, for example, if we will make much more forests. Because there are some projects in China, in Sahara and so on, with forestation and so on. Of course, it will consume a lot of carbon dioxide.
The hope in the forest is, let's say, limited. By many factors. One of them is you need to actually grow the tree, not just plant it. Also, the sequestration in the biomass does not hold forever. So, yes, the trees can help, and I would love to have a quantification of how much, but the main part still remains the same: stop using fossil fuels where it's possible. Perhaps to add to that, I think this kind of reforestation and changing the agriculture efforts are much more important for the biodiversity and basically for the health of the landscape than as a mitigation way for the climate change.
Thank you very much. Ondráš Přibyla and Jan Krčál. Thank you. And let's move to our last lecture. Last but not least is going to be about energy industry, society and climate change. Please welcome Oldřich Sklenář from Association for International Affairs.
Thank you. So I hope it's on or not? Not yet? Yeah, now. Thank you, and thank you, Mr. President, for invitation. It's really an honor to be here. So today, maybe the previous slide, thank you. Today I represent here the Association for International Affairs, where usually I focus on energy industry and its emissions. But today I will talk also about energy, but from, let's say, different point of view. So this presentation will be a bit different from the previous ones, let's say, because in my slides there are not practically no notes, so I will use the help of my computer. I hope that it still has some energy. I will see. Yep. Okay, so and I will sit. Thank you for understanding. First slide, and maybe yes, I can use this one too. Perfect. Okay. Yeah. Okay. Fossil fuels. How did it started? Once upon a time, there was a man who happened to find some strange dark stone. Today, we no longer know how it happened, but obviously, he had somehow found out that this dark stone could burn so well, it can actually replace wood used for heating or cooking. This happened more than 5,000 years ago in ancient China, and according to the archaeologists, it was the first use of fossil fuels for energy purposes. So today, like more than 5,500 years ago, today we can say that we gained most of our current wealth thanks to the fossil fuels. Let's say that our economy is still based on fossil fuels. We are using them to heat our homes. We are actually using them to produce the food we eat, to commute every day, and of course to produce electricity for all different electronic devices we are using, including this microphone, this computer, and those lights. As you know, unfortunately, there is a catch. This catch is named carbon dioxide and other anthropogenic greenhouse gases, which induce climate change, which has the potential to turn lives of this and further generations completely upside down. Well, of course, there are like more catches. One of them is support of non-democratic regimes from which we buy these fuels and some different aspects. But let's say that this one is and will be for the next generations the biggest challenge. Now the question is what to do, how to get out of it. The answer is simple: just to don't use fossil fuels, which sounds easy, but as you know, it's not. So where is the problem? The problem is that that so far we haven't figured out how to replace fossil fuels. The fact is that despite all of the new technologies, all of the progress, we still heavily depend on them. You can see this graph showing not electricity production, but primary energy sources worldwide. And you can see that still the biggest share is the fossil fuel still has so far bigger share than possible alternatives. So what to do now? Like what's actually the point? The point is the issue is that we need to rebuild the complex way we manage energy, or more precisely energy resources. Why? Why we cannot go business as usual? Well, one of the reasons, and it was already mentioned, is that fossil fuel alternatives, I mean, for example, renewables, has some unpleasant limitations, like low energy density, or intermittent production, plus, and it was also mentioned, they need time to build them. So we cannot just replace those sources by the alternatives, because we don't have time for that. Another reason is that the way we are managing with energy resources now is actually quite poor. Maybe some of you know the concept of energy slave. And according to this concept, each of us is using equivalent of work of several hundred to several thousand non-stop working slaves Depends on country, it depends on methodology, how you calculate that. The question is how it's possible. It's also due to the our system of dealing with energy is quite ineffective. And I'm talking about the previously mentioned areas. I mean, everybody understands the importance of financial management. It's something you don't need to explain, but actually not everybody is thinking about the energy management within the same framework. I mean, there is a lot of focus on the revenue side, how to produce the energy. But often we completely ignore the expenditure side, how we are using this energy. So one practical example on this slide, you can see differences between a standard building on the left. Okay, no. Yes, that's like current energy consumption, and on the right there is energy consumption of a passive building, of the passive house. As you can see, you can actually, by use of different technology, can save up to 90% of energy. The problem is that currently in the Czech Republic there are like less than 10,000 passive houses compared to several million other buildings. And as I mentioned, we actually don't have time, not only time. In some cases, we don't have manpower to rebuild all of those buildings to reach the same efficient way. So the question is actually how we are dealing with the existing buildings. It was mentioned like a couple of minutes ago. Those are results from survey from 2019 with the question on indoor heating temperature. I think that it was made on this survey made on sample of more than 500 inhabitants. And surprisingly, the most common answer was that those people are heating their buildings, their houses they're living in on temperature between 21 to 25 degrees Celsius. Which is quite far from the recommendation, which is somewhere between 18 and 20. And it was mentioned each degree of Celsius is approximately 5 or 6% of energy. So you can see that we are like in a lot of cases we are far from the optimum temperature. Imagine that those houses will be heated by electric heaters. So then you have to count not with this like 25+% of energy losses, but you also have to count with in the current energy electricity production system. You have to count with like more than 2/3 of losses during the transformation process. If we will replace our current coal boilers or nuclear power plants with some renewables, the situation will be a bit better. But then we need, on the other hand, some systems for storage with also not best efficiency. It's important to think how we are dealing with energy now. The similar situation it's with transportation. maybe most of you know that in case of internal combustion engine, the power-to-wheel efficiency is less than 25%. The rest are losses. Of course, that if we will use electric car, the efficiency is higher, but then we need to count with efficiency of electricity production. Maybe in those cases is sometimes better to think out of the box, because of course that from point of energy efficiency or energy use, the most efficient way is to use a different mode of transportation. I mean, to don't use a personal car at all. In this case, the change, the energy saving will be much more challenging because availability of this alternative transportation modes is limited, and it's influenced by existing infrastructure. It's also about the way how we are, for example, designing our cities. It's about the urban planning. Because current situation when we have to deal with some low density satellites around the cities, that's actually the worst case from this point of view, because then those inhabitants have to use personal cars. In case that we will do special or urban planning a different way, we can work with blocks, so-called 15-minute city, which prefer walking or bike riding instead of cars. Another example of let's say energy wasting, it's also the way how we obtain animal proteins. Yeah, it's correct. I mean, I'm talking about the fossil fuels. So actually the current situation is that first we use fossil fuels to produce fertilizers, to produce crops, and then to waste most of those crops on metabolic processes of livestock, which then we consume, in some cases overconsume, to suffer from obesity. That's also something which is not maybe not very well known. That I'm not sure if you can see it, but the efficiency of protein production is from like 3% in case of beef, up to like 17% in case of poultry. The rest is the body heat which the animals need to live. But it's from our perspective, it's kind of wasted energy. Maybe the biggest problem is that our demands are growing. We are heating or cooling larger and larger areas or houses. There actually also increase number of flats or houses. We are using personal cars more and more. When I check the statistics in Czech Republic, there is like increase by 1/3 of registered personal cars in last 10 years. And that's something which is not sustainable in long term. Because when we are struggling with alternatives, how to produce energy alternative way, we cannot continue in such a growth. And actually, none of these examples of growth is necessary for a good life. actually those consequences of these increased consumption complicate solving of the problem we have. Maybe some of you remember Zeno's paradoxes. In this case, what you can see on this graphic is the one about Achilles and the tortoise or turtle. The point is that Achilles is just a few steps from a turtle. But he actually can't catch up with the turtle because whenever he's tried to approach the turtles make a few more steps. And we can be in the similar situation with our attempt to reach zero carbon economy. Because once we set some goal, we can realize that that it's simply not possible to reach because of this overconsumption. So what I just want to say is that energy and related emissions is not just a question of energy industry. The problem of the issue of rising consumption should be addressed across to the sectors. So not only energy, but also transportation, agriculture, etc. Decarbonization of energy production is and it will be difficult. So we have to facilitate it through a systematic effort to reduce consumption. This includes not only technological but also organization changes or changes in consumer behavior, because otherwise we'll be simply not able to reach zero carbon economy. Yeah, so that's all for this moment. So please. If you have any question. Yeah.
Thank you, Audrey, thanks. Is it on? Yeah. Thanks, Audrey, for your talk. Now, we're scientists, so we like to put numbers on things, and that's maybe also a question to you guys. So, let's say we change our lifestyle. We really behave as we should. We're all vegetarians, take public transport, don't overeat our houses, and do all this together. How much will this reduce out of the consumption that we're doing right now? How big part of this will it be from this whole 100% that we need to reduce? I mean, are we talking, will this be 50% of the problem? Will it be 10% of the problem? 1% or 70%?
Yeah, it's not so big numbers. Actually, there exist infographics and on a website on facts about the climate, and there are no like 50%. Maybe András will try to find it, but it's not definitely not small numbers. And when we need to reach early zero carbon economy, it's part of the solution which actually cannot be skipped. I mean, first things first. So now at this moment we have to focus on transition in energy sector, but in the future we just cannot. Probably it's not online. Okay. Yeah. Okay. So you can easily find it, and as I said, those numbers are not like tens or dozens of percent, but they are still significant.
Thanks, and don't get me wrong, I think it's good to change behavior, but also it's good to have the numbers.
Thank you for your talk and for all the data that you gave us. In front of us, you produced very interesting schemes, And I wonder what your opinion is on the future of cogeneration of electricity and heat, which increases the efficiency of energy use in thermal and nuclear power plants, especially that you use the heat which is created in both types of power plants for just transported somewhere where it can be of use.
Yeah, it's managing with heat is also part of energy management, and it actually we can also use low potential heat. There is no necessity to produce in the future to produce heat from like coal power plants when we will be able to close energy loops. I mean, in the current situation, when, for example, when I will take a shower, then I can use the water, and this hot water just disappear in the sewage system with a lot of this, with most of this energy which I before that use to heat this water, and actually we can use this energy again. We can use it with use of heat pumps. There, of course, that there will be some losses, but we are talking. Actually, there is, I think, that in current climate plan of City of Prague, there is mention that by this technology of a heat pump placed in a water sewage plant, it can has a thermal output of like around 250 megawatts. Which is a lot. So as I said, important is to and now I will repeat myself. As we know, financial management is important to calculate not only on the production side, but also with the consumption side, and in best case to close mentioned energy loops and to use as much as possible this so-called waste energy, which shouldn't be wasted in the future.
Well, thank you. I just know that in the 90s, Professor Moldan proposed as Minister of Environment to transform all heating plants in cities which produced centrally heat for central heating, to produce them into cogeneration units that would produce also electricity, and vice versa, attached thermal units to power plants. And in that way, the estimate was that the efficiency of these systems would increase from 30% to 70% of the energy input. Thank you.
I have just one comment to the question of Pavel. I don't know how much is it in energy consumption in relation, but the annual estimates for the last years are about 2 billion tons produced in the world of the wastes, and about 800 million waste of the food waste, which we produced annually, which of course are terrible numbers.
They are, I didn't mention it, but yeah, I totally agree with that.
Well, I would, if I'm allowed at this later hour, I would be a little bit skeptical. You know, if I understand correctly, what your association is doing is trying to push for societal change through a decreased energy consumption in order to get some percentage of CO2 saved. I don't think it has a chance to work. Europe, as much as I understand, is responsible for about 9% of all CO2 that's produced. USA is a little bit more, but China, India, and other places on this world, that deserve to get to similar standard of living as we are enjoying, that deserve to have air conditioning and enough food, will not save CO2 this way. So this is a very, very incremental way of change. That, on the other hand, by political push for these measures, could actually lead to societal changes that will be very strongly against anything that has anything to do with CO2 decrease. I think we might pay a huge political price for very, very incremental change of CO2 production. I am strong techno-optimist, and I strongly believe in smart solution. And I think that's why we are here. You know, that's what learning society should do, what Europe should do, because we can't really do much with our 9% part of the CO2 production. We can do a lot with our fantastic universities and great research centers. So what we should do is to find smart solution. I really do not think that we should concentrate on decreasing the consumption. I don't think this is the way. Thank you for listening to my remark.
András would like to react. Yeah.
Please go ahead. So one comment, the scale of a problem and the structure of a problem are two important aspects. Scaling the problem, which is what Oldřich was speaking about, trying to reduce consumption, is not changing the structure of the problem. And so to look at the structure of the problem of emissions, and I'm just picking emissions of greenhouse gases, not all the connected problems of biodiversity loss and all the others. But the structure of CO2 emissions for Czech Republic is following. And basically most countries in Europe will have a similar structure. We have something like 12 tons of CO2 equivalent per person per capita. Out of this, 40% is electricity and heat generation. And these big chunks are single power stations, the lignite power stations, and no single person has a switch of the power station. So this is something we cannot do individually. We need to change the structure of the energy electricity system, and we can't do it as individuals. We need a society to change that. Then some 15% is transportation, and most of it is our cars. 10% are cars, 5% is buses and trucks, and just 1% is flying. Again, this is something, well, this we can change a bit.
I came by bike.
Great. This we can change a bit, but my take here would be the biggest change would be the structure of public transport that is available. Again, this seems to be more a structural problem, and I can't buy the fast train from Prague to Brno, and this will be changed only then by state. This is industry, and this is industry. Here, this 10% is what we can change by consumption in our households. So the structure of a problem is not so much depending on individual behaviors. It's on the system we are living in. By the change of your consumption habits, you can reduce these 12 tons to something like 7, and the rest of it is because you live in the Czech Republic that has such inefficient or such a greenhouse gas intensive electricity generation and so on. So what I want to point out is the difference between the scale of a problem and the structure of a problem. And I think you are right in the point that we will not change the scale so much. We need to address the structure and address it as a system, not as individuals trying to live as hermits.
Well, I don't think that we need to live as hermits. But anyway, there is also ethical perspective. We cannot ask somebody else to just stop growing while we have such a consumption. At this moment, and also in the past we also developed some ways with carbon trading, with restrictions on car emissions, which then are adopted practically worldwide. So it's also about the good cases or best cases which we can offer to provide a solution for this issue.
Okay, thank you very much. Our time is off. So I would like to thank all our speakers. We were delighted to have here today Professor Jutta Hansen. Thank you so much. Professor Andreas Dreisler, both are from the Darmstadt University of Technology. Thank you very much. Ondráž Přibyla and Jan Krčál, representing the facts on the climate change. Thank you. And Oldřich Sklenář, Association for International Affairs. Thank you. And thank you all for coming and for asking the questions, and thank you for your interest in science and future of energy. Have a nice rest of the day.